consider the cis and trans isomer. Say 1, 2 or 2, say 2, 3 dichlorobutene, but2ene. Okay, this compound, we can write this compound as C double bond C CH3 Cl. This one is 1, carbon number 1, 2 Cl, and again in 3 again a Cl, and here is CH3. So the compound is, this one is 1, 2, 3, 4, that is 2, 3 dichlorobutene. So the molecule can be represented in this manner. Again, the molecule can also be represented like this: Cl double bond Cl CH3. So here the same group are on the same side of the double bond. Okay, CH3, these are also the same group in the same side of the double bond, and here the same groups are in opposite sides of this double bond. The same group are in opposite side of the double bond. Where the same group are in the same side of the double bond, this geometrical isomer is called cis isomer, and when the same group are in opposite side of the double bond, the isomer is called trans isomer. Okay, so here we can say that 2, 3 dichlorobutene has two geometrical isomers, and they are cis and trans. Now let us have some other examples. Now we have a compound pent 3 in 1 ine. So 1 ine means triple bond. Then this one is 1, 2, 3, 4, 5. 3 in double bond between 3 and 4 carbon. And here number of hydrogen, there will be just 1, here nothing, here 1, here 1, 2, 3, 4, and here C is 3. So we need to take the double bond C, that is carbon number 3 and 4. Okay, now the groups present in carbon number 3 and 4. Carbon number 3, a hydrogen is present. We have written this hydrogen like this, and the other group is that group, that ethyne group, HC triple bond C. Okay, and here in number 4 again a hydrogen is present, and other is CH3. So the molecule can be represented by this, and you can also write this where two hydrogen are in opposite sides of the double bond. So C double bond C, here is hydrogen, and here is that ethynyl group HC triple bond C, and here CH3, and here hydrogen. Okay, so here the same group are in the same side of the double bond, so this geometrical isomer is called cis, and here the same group are in the opposite sides of the double bond, so this one is trans. So the compound pent 3 in 1 ine may have two isomers, and there are cis and trans. Okay, let us check another example. Pent 1 in, just pent 1 in. Now pent, 5 carbon atoms there, 3, 4, 5. 1 in double bond is here, so here two hydrogen atoms are present, so H and H. Here only 1, again 2, 2 and 3. The question is whether pent 1 in may have any geometrical isomers or not. Of course not, because the double bonded carbon here has a symmetrical shape. Here all the groups are same hydrogen, two hydrogen atoms are present, and that's why this is a symmetrical carbon, and therefore no geometrical isomer will be there. We can see that if you write in this manner, hydrogen, hydrogen, double bond C, then here hydrogen, this hydrogen, and the other is propyl group, that means C3H7. And how can you write this? By changing the position here, the same group on the same side, or the same group still in the opposite side also. Since in the same side, if we take this, so this will be cis, and if you write in this manner is hydrogen, hydrogen, C3H7 and hydrogen. This is also the same thing. Okay, this one is also cis. So the compound pent 1N should not have any geometrical isomers. Okay, let's check another example. 1-chloropropene, 1-chloropropene. So 1-chloro, 1-propene, actually Cl in one position, hydrogen in double bond C, then other three hydrogen, other three carbon atoms are there, and here a hydrogen is also present. So here hydrogen, and then the other 5 carbon, that is C3H7. Oh, this is propene, sorry, this is propene. So only 3 carbon, 1, 2, and here CH3. So this can form a geometrical isomer as 2 hydrogen atoms are in opposite side, and they may be on the same side of the double bond also. So this one is a trans isomer as the same group is opposite side of the double bond, and the cis isomer is like that. Here same group are on the same side of the double bond, so this isomer is cis. Okay, so 1-chloropropene must have 2 geometrical isomers, they are cis and trans. Okay, let's check the next example. But2-ine, but2-ine. Now where there is a triple bond, no geometrical isomer can be formed because the molecule is linear. 2-ine, 1, 2, 3, 4, 2-ine. So this one is CH3 and this one is CH3. So this is a linear molecule. This is a linear molecule, therefore no geometrical isomer. Okay, so ine may not have, if there is no double bond, no geometrical isomers will be there. Okay, so but2-ine cannot have any geometrical isomers. The next is 2-methyl-but2-ene. If it is 2-methyl-but2-ene. So what is the structure? 2-methyl-but2-ene. Say 2-methyl, that means CH3 and a double bond also, and this one is CH3. There is another CH3. Here a hydrogen is present. So can this compound make any geometrical isomer? Let's check. CC double bond, C double bond C. Here 2 CH3 groups are present. So this is a symmetrical, or the molecule has a symmetry, a plane of symmetry. Since the molecule has a plane of symmetry, so no geometrical isomers will be there, as the molecule has a plane of symmetry. Okay, since same group are present on the same double bonded carbon, the molecule has plane of symmetry, and therefore it will not have any geometrical isomers. Okay, let's check another. Now the next topic is aromaticity. The next topic is aromaticity. Now, what is aromaticity? Aromatic molecules in organic compounds, aromatic, to be aromatic, the conditions are: number 1, the molecule must be planar, must be cyclic, and it must have 4n+2 number of pi electrons. So the first condition is molecule must be cyclic. Number 2, molecule must be planar, and number 3, molecule should have 4n plus 2 number of pi electrons. Molecule should have 4n plus 2 number of pi electrons. If all these three conditions are maintained, therefore we can say the molecule is aromatic. Where n equals to, and may have 0 value, 0, 1, 2, 3, dot dot dot. Okay, now let's have some example like this molecule. Okay, first of all, you have a positive charge is there. First of all, the molecule is cyclic. Okay, the first condition is maintained. Number 2 is the molecule is planar. This all carbon, 1, 2, 3, 4, these 4 carbon atoms make double bonds, so therefore must be sp2 hybridized. Now for state of hybridization sp2, the shape is planar, trigonal planar. Therefore all these carbons, since they are sp2 hybridized, as they made a 3 sigma bonds, one is here, another is here, and the other one is here, a hydrogen is also present. So 3 sigma bonds, each of these 4 carbon atoms has made 3 sigma bonds, therefore sp2 hybridized, and sp2 means planar. So all these 4 carbon atoms are planar. Now let's check about this carbon. The carbon, if there is no double bond, if no positive charge was there, then it must be sp3, and a plus charge means one orbital is eliminated. So sp3 minus 1 p orbital, so sp2. So this carbon is also sp2 hybridized. Okay, therefore all these 5 carbon atoms are sp2 hybridized. That means the molecule is planar, the molecule is cyclic. Now the total number of pi electrons present, the pi bond is 2, each bond carries 2 electrons, therefore total number of pi electrons is 4. 4 means 4, n equals to, for nothing 4 comes, so this is not aromatic. Okay, if n equals to 0, it comes 2, if n equals to 1, then 6, if n equals to 2, then 4 to 8 plus 2, 10. So if 4 electrons are present, the molecule is not aromatic at all, so it is a non-aromatic. We can say it is a non-aromatic. But another thing is there, if the molecule has 4n number of pi electrons, 4n pi electrons, then the molecule is anti-aromatic. Okay, if the molecule is cyclic, if the molecule is planar, and if it has 4n number of pi electrons, then it is anti-aromatic. So here we get 4 number of pi electrons, and here the value of n is n equals to 1, 2, 3, dot dot dot. So here n equals to 1 means 4. So if 4 pi electrons are present in a cyclic and planar molecule, the molecule is anti-aromatic. So we can say that this molecule is anti-aromatic. Okay, now the next example is this: negative charge, double bond, double bond. Whether it is a negative charge or a positive charge, it is sp2 hybridized. So all these 5 carbon are sp2 hybridized, that is all are in the same plane. The molecule is cyclic, the molecule is planar. But next condition is whether it has 4n plus 2 number of pi electrons or 4n number of pi electrons. If this negative charge get delocalized, since it is in conjugation of this pi bond, if it makes a double bond here, the pi bond shifts to this carbon. So a resonating structure or canonical structure may also be formed, where the double bond is placed here and a negative charge is here and the double bond is here. So the negative charge here, the negative charge can get into delocalization or can get into resonance. Therefore we should count this negative charge as pi electrons, a pair of pi electrons. Therefore the total number of pi electrons present is 1, 2, 3, 4. Each bond carries 2 pi electrons. So 2 pi bonds means 2 pi electrons, and a negative charge means 2 pi electrons. So total number of pi electrons is 1, 2, 3, 4, 5, 6. So 6 pi electrons. If n equals to 1, then 4n plus 2 means 4 plus 2, 6. Therefore this molecule is aromatic. Now let us check some other example also. The next molecule is, now we need to say whether this molecule is aromatic or anti-aromatic. Here all the carbon atoms are sp2 hybridized, as all made double bonds, so all are sp2 hybridized, sp2, this one is also sp2. So the molecule is planar, the molecule is cyclic, the molecule is planar. And the next one is how many electrons? Pi electrons are present. Only 2 pi bonds are present, therefore the number of pi electrons is due to the 4 pi electrons. So where 4 pi electrons are present, that is, it is maintaining the 4n rule, so the molecule is anti-aromatic. Anti-aromatic in nature. Okay, so we will have some other examples on aromaticity in our next video.